Hi guys, Gibson here. Today we're going to do our first lesson in this new unit on rational functions. And today we're going to talk about this concept of inverse variation. How do two variables vary inversely to each other? What does it mean to do that? Okay, so let's look at our objectives here. So the first one is we should be able by the end of this lesson to identify when we have direct or inverse variation. So direct you've actually seen before. That's, think of linear variation or linear function, which we studied at the beginning of the school year. Okay, but we're going to compare the two. What does it mean to vary directly and inversely? The second is, if I give you enough information, can you write the function to model inverse or direct variations? And then the third is to describe what we call combined variation. So if you have, say, more than two variables, you could have a function where two of those variables vary directly with each other and the other two vary inversely with each other. So we would call that combined variation. Okay, so we'll work with those a little bit. All right, let's start by looking at this example here. Okay, now you probably don't ride bikes much anymore, but let's suppose you did, and you wanted to figure out how much time would it take you to ride 24 miles if you were riding at different rates. And rates is just another word for speed, right? The rate here would be in miles per hour. That's usually how we measure speed, right? Certainly in a car. So let's pretend that we're riding at 2 miles per hour. How long would it take us to travel that 24 miles? Well, if we ride 2 miles in 1 hour, right, we're going to have to divide the distance 24 by 2 to get the time. And if we did that, right, we would get 12. So here's really what we're doing, right? Time equals distance divided by the speed. So let's plot that point on our graph here. Okay. Now, 2 miles per hour, that would be a very slow bike ride for a very long time, right? But let's speed up a little bit. So what if we're doing 3 miles per hour? Well, 24 divided by 3 gives us 8. So let's plot that. Same thing, let's just keep going here. Now if we continue to speed up to 6, 24 divided by 6 gives us 4. 24 divided by 12 gives us 2. And 24 divided by 24 is 1, right? If we're going 24 miles per hour, it will take us 1 hour. Okay, so let's put that on the graph. So what shape or curve do we get if we try to fit a nice smooth line through those points, right? It's going to look something like that. Now, you may say, that looks like exponential decay. And you're right, the graph does kind of have that appearance to it. Mathematically, it's a different type of function than exponential decay, and you'll see that in a minute here as we start to actually write the function for it. But it has some similarities. You notice it will have a horizontal asymptote, right? As we go faster and faster, the time will get shorter and shorter, but it will never go to 0 unless we were going infinitely fast, right? There's a limit to how fast we can go in the physical universe. So let's let our bike rider take that path. Let's see if he comes back here. Up there he comes. So this relationship in terms of how do speed and time vary with each other, what we've described here and what we've graphed here is what we call inverse variation. And we call it inverse because as the speed increases, the time decreases. In other words, if one of the variables is getting larger, the other variable will get smaller. We call that inverse variation. Or it works the other way, right? If one of the variables gets smaller, the other variable will get larger. The key is that they're going to move in opposite directions, right, as we change the values. So let's continue working with this a little more here. Here's our graph that we created. And here's the equation, right, that we use to calculate the time. Let's see if we could actually write this so it looks more like a function. So if we think about the time, right, that's our y variable. So we're going to replace that with y. If we think about our speed or rate, that is our x-axis or x variable. So we can rewrite this replacing time and speed with y. and x. And the distance for this particular problem, right, was 24 miles. So we'll put that in for the distance. Okay. So in this function that we just wrote, right, this looks like a function, y equals 24 divided by x. The 24, right, remains constant, right, for this particular problem, right? We came up with all these different x and y values, but they all assumed that we were traveling 24 miles. So we call that the constant of variation. So here's a little graphic just to help remind us, right, what this is really saying, right? As x gets larger, think of it as taking 24 and dividing it by a larger and larger number. What's going to happen to y? Y is going to get smaller, right? Or as x gets smaller, we divide 24 by a smaller and smaller number, y will get larger. So you can see graphically how this inverse variation would look. As one increases, the other decreases. Okay. Now, we could rewrite this equation to solve for x, which would be the speed, right? So we would take our first equation, divide both sides by x, and then divide both sides by y and multiply by x. So it's the same relationship. It's just simply being able to solve for x, or speed in this case. And we could write it one more way, right? Put x and y on the same side, and this would allow us to solve for the constant. I'm going to go ahead and close out my window here so it doesn't block the screen. If I can do this, there we go. All right, so let's officially define here this concept of inverse variation. It says we can model an inverse variation with the equation x times y equals k. So this is the exact form, right, that we used in the previous example. X represented the speed, y the time, and that equaled our constant 24. So we call that k the constant of variation. And you can see the other two ways we could rearrange that equation. So either solve for k, solve for y, or solve for x. They're all equivalent. It just depends which variable we are trying to find. Okay. So the constant of variation for k, let's say I didn't give you that 24 up front, but rather just gave you these sets of x and y values for rate and time. How could we find the constant of variation, the k value? Well, if we went ahead and plugged in, right, x for rate and y for time, multiplying those two is equal to k. So we can take any one of the pairs of x and y values that we had for rate and time and plug those in. So let's, for example, pick 6 times 4. 6 times 4 is 24, right? We get our k value of 24. But we could have picked any of these others, right? 2 times 12 is 24. 3 times 8 is 24. 24 times 1, obviously, is 24, okay? So we can find our k value if we have a set of x and y values by simply multiplying x and y together if we have inverse variation, right? So here's how we could write this once we find the k value. So same thing we had on the previous slide, right? And we could rewrite it this way, solving for y or the time. All right. So in summary, inverse variation we could write as y equals k divided by x, right? And what that means is as x gets larger, y decreases, right? So they're going to move in opposite directions. And the graph is always going to look something like this nice smooth curve. Direct variation, we can write this way. Now, this should look familiar, right? Y equals kx. This is a linear relationship. And what this means, as x gets larger, we're just multiplying by our constant k, so y also will get larger. So direct variation, they move in the same direction. If one gets larger, the other gets larger. If one gets smaller, the other gets smaller, right? So if we graph that, we're going to get a nice linear function, nice straight line here. So whether it's inverse or direct, we will still have this k as our constant of variation. And we can, for any given problem, we can work to solve for that value of k and then be able to write the function, whether it's an inverse variation or direct variation. Now, direct variation, hopefully you recognize that if that's a linear function, our k value basically is our slope, right? Remember the slope-intercept form, y equals mx plus b. So in direct variation, we have a k value that's basically our slope. And the way I drew the graph below, right, our y-intercept is 0. So our b value is 0. It kind of drops off. And we're left with kind of the simplest linear function we could write, right? Y equals kx or y equals mx, if you want to think of that as the slope. All right, let's look at an example here. I'm going to give you some x and y values, and you're going to have to determine, is this an inverse or direct variation, or perhaps neither, okay? There's lots of other different types of variations besides inverse and direct, right? We just studied exponential variation between different functions. And then once we figure out what type it is, we want to write a function to model that variation. So what would the steps be? Well, first, let's look at these values. Can we recognize whether we have inverse or direct variation? So notice our x values are increasing, right? 1, 2, 6. So now the question is, what is our y values doing? Well, they're going from 3 to 6 to 18. So the y values are also increasing. So what type of variation is that? If x increases and y increases together, then that would be, right, direct variation. So what form would we use to begin to write a function if it's direct variation, right? Well, here's a form that we just had from the previous slide, y equals k times x. So now to be able to write the function, make it complete, we need to define what the value of k is, okay? So we could rearrange this, right, to solve for k, and for direct variation, it's simply y divided by x. So let's take these values that we have in our table and plug them in to see if what our k value is. But here's the important thing, right? In order for this to be a direct variation, we need to have the same k value for any pair of x and y values that we plug in here. So we need to check all of them. We can't just check one and then assume the others will give us the same k value. If it doesn't give us the same k value, then that means we don't have a direct variation. And you'll see that holds true for inverse functions as well. So here's what it would look like, right? If we plugged in all three of those values, y divided by x. So 3 divided by 1, is that equal to 6 divided by 2? Is that the same as 18 divided by 6, right? Now, in this case, right, all of these fractions would simplify to 3, right? So since we get the same value for all sets of data for k, then we could say, yes, we've confirmed our initial assumption that it's a direct variation. And now we can use that to write the function. So we would just say y equals 3x, okay? So 2 parts here. What's our first assessment, right? Does it look like it's direct or variation? And then we find the k value, and that will help us to kind of prove that it is indeed direct or inverse if we always get the same k value no matter which set of x and y values we choose to plug in. All right, let's try another example here. So again, our x values are increasing, 1, 2, 6. Okay. What's happening to our y values? 18, 9, and 3, they're decreasing. So if x is increasing while y is decreasing, what type of variation is that? That would give us a inverse variation. All right, so we want to find the k value in order to write the function. So now we're going to use this form for an inverse function, right? It's really important in your notes to keep this straight, right? What form do I use for direct to solve for k? What form do I use for inverse to solve for k? So for inverse, it's x times y equals k. So which means we just simply need to multiply the x and y values together. So let's do that. We have 1 times 18, 2 times 9, 3 times 6. Those all give us the same k value of 18. So we've confirmed that it is inverse variation since we get the same k value. And now we can just simply plug in that value of 18 for k, and we have written our function for this inverse variation, x times y equals 18. If you wanted to change that to the other form, you could say y equals 18 over x. All right, let's see if you can do this one here, okay? I'll just pause for a second, see if you can pause it and figure out whether it's inverse or direct, and see if you can find your k value. All right, so x values are increasing, but so are the y values. So that means it appears to be direct, right? So let's find our k value. We're going to use y equals k times x, but if we want to solve for k, right, we would write it in this form, y divided by x. So let's plug in those values. 18 divided by 12, 21 divided by 14, 24 divided by 16. Okay, and let's see what we get for our k value here. So we just have a bunch of fractions we need to simplify, right? But they all turn out to be 3 over 2, or if you used your calculator, you would get 1.5. You know me, I like to leave things as a simplified fraction, okay? So this confirms that we do have direct variation, and our k value is 3/2. So now we can write our function for direct variation as y equals 3/2 times x. We plugged in the value of 3/2 for k. All right, let's try one more together here. All right, so x is increasing, right? 0.5, 2, and 5. Y is decreasing. So this appears to be inverse variation. Sorry for the dog, he's barking at something. So we want to find our constant of variation, assuming that's inverse variation. So we start with x times y equals k. And now let's multiply, right, each of the x and y values together and see what we get. So 0.5 times 4, 2 times 1, and then 5 times 0.4. So what do we get if we do that? Well, we get 2 for all of these values, okay? So that confirms we have inverse variation. And we can write our final function, y times x equals our k value of 2. All right, one more. You're probably asking, well, what happens if we don't get a k value? Well, let's look at a problem where that occurs here, okay? I think this is one where it occurs. Yes. Maybe, we'll see. I can't remember. All right, so x is increasing. What's happening to y? It is decreasing, right? So inverse variation. So we're going to start with x times y to find our k values. So let's plug all those in. So we get 1.4 for each of these. Okay, this is not an example here. We'll go through this one pretty quickly. I think I have one more where they don't come out to the same k value, right? So here's our inverse function, x times y equals 1.4. All right, here's one. Let's do this. So x values are increasing, y values are decreasing. So it appears to be inverse variation. So let's find k. Now we're going to solve for k, right, as x times y. So let's multiply these together. 1 times 2, 2 times 1, 3 times 0.5. And here, right, the first two give us 2, but the third one gives us 1.5. So we don't get the same k value for each of the 3 sets of x and y values. So even though it looked initially like it was inverse variation, this is a case where we can say it's neither direct or indirect because we don't have a consistent k value with all of the different x and y sets. What type of variation is this? I don't know. I don't know if it even has a name, right? I kind of made up these numbers, but it's certainly not a direct or indirect variation. All right, let's move on. We're going to talk about this concept of combined variations, okay? So quantities can vary with respect to each other in different ways, right? So if I wrote a function like this, how would we use words to describe this variation? Well, we have y equals to k times x. Now, it's not just x, it's x cubed. That's okay. But what form does that give us, right? This is the form for direct variation, if you look back in your notes. And here, from words, we would say y varies directly with x to the cube. In other words, if x to the cube gets larger, then y will also get larger. And vice versa. If x to the cube gets smaller, y gets smaller, right? How about this one? We have y equals k divided by z squared. How would you, in words, describe that variation? Well, notice we have a variable in the denominator. That's a clue that it's going to be inverse. So here we would say y varies inversely with z squared. Okay, we'll just use that whole thing, z squared, as the value that it varies inversely with. Now, what if we combined direct and indirect, or multiple variations within one function? So let's look at this example. We have z equals k times x times y. Here we have three variables, right? Z, x, and y. Remember, k is our constant. We're not going to treat that as a variable. So we have three different variables. How do they vary? How do each of them vary with z? Well, we could cover up, right, y. So if we just had z equals kx, we would say, oh, it varies directly with x. And we do the same thing with y. We'd say, oh, it varies directly with y. So if we were to describe this in words, we could say it this way, right? Z varies directly, you could say with the product xy, or you could say directly with both x and y. Okay, either way would be a good way to describe this variation. Let's look at a couple more here. Z equals k times xy, so the same as what we had above, but now we have divided by w. So we've got four variables here, right? Z, x, y, and w. K is our constant. So how would we describe this variation? Well, z varies in two different ways, right? It's going to vary directly with the product of xy, just as we had above. But with the w in the denominator, that's going to tell us that z varies inversely with w. So here's how we would say that. Z varies directly with the product xy and inversely with w. So this is an example, both of these are, of a combined variation. We can have more than one variable that varies, and they can both vary directly. One could vary directly, another could vary inversely. They could both vary inversely, right? There's really kind of unlimited different combinations that you could think up here and write functions for. Let's do one more here. Z equals k times w divided by xy. So remember, if the variable's in the numerator with our k value, that's going to be direct. If the variable's in the denominator below the k value, that's going to be inverse. So this one we would write z varies directly with w and inversely with the product of xy, or you could say inversely with both x and y. All right, let's do a few for you to practice here. So I'm just going to pause for a second and see if you could describe what the variation would be in words. Okay, this one would be y varies inversely with z squared, because we have z squared in the denominator. This one, we're multiplying y squared by our constant k, so this would be direct, and we would say y varies directly with y squared. Now here, there's no variable in the numerator multiplying k directly, so we won't have any direct variation. We have w and z in the denominator, so both of those would vary inversely with x. So we'd say x varies inversely with the product of w and z. And one more here. Nothing in the denominator, so this will be direct variation, and we describe it as z varies directly with the product of xy, or x times y. Okay, So you need to be able to look at any given expression with multiple variables and figure out which ones vary directly and which ones vary inversely. And the clue is it multiplying k in the numerator? If so, direct. Is it dividing k in the denominator? If so, inverse. All right, let's look at one or two other types of problems that you'll have on your assignment today, and then we'll wrap this up. So it says, suppose y varies inversely with x. Okay, so they're telling us that x and y has an inverse variation. It says, write a function that models each inverse variation. Then find y when x equals 10. So to write a function, we have to be able to find the k value. And to find the k value, you're always going to have at least, right, one set of x and y values that go together. Okay, so since they already tell us that it varies inversely, let's get my highlighter going here. Right, it tells us right here, y varies inversely with x. Okay, so we don't have to figure out, in this case, whether it's inverse or direct. We really don't have enough information. We only have one set of x and y values, right? So we can't really determine, are they increasing or decreasing relative to each other. So if it's inverse, right, then we could go ahead and start with this, y equals k over x. That's the general form. But we want to solve for k, right? So we're going to rearrange that so we can find k by just multiplying x and y. So what are we going to plug in for x and y? Well, that's where we're going to use these values, right? We're going to take 20 and plug it in for x, and we're going to use a different color here, 5, right, and plug it in for y. Okay, so 20 times 5 gives us 100. Let's get this color updated. So we have our k value, right? K value is equal to 100, so we're going to go back to the original form and plug in the 100 for the k value. So don't forget to do that when I ask you to write the function, is put the k value back in there, okay? Okay, the second step, it says, find y when x is equal to 10. So that's really simple. We're just going to take the function that we just came up with and just plug in 10 for x and solve for y. So we get 100 divided by 10, which is 10. Okay, simple once we have the function. All right, let's try one more. Suppose y varies inversely with x. Okay, so again, we don't have to guess. It's telling us, right, that it varies inversely. It says write a function that models each inverse variation. So start with our general form, solve for k, and then multiply 6 and 3 gives us 18. So here is our function, y equals 18 divided by x. Now, the second part says find y when x is equal to 9. Really simple, right? We're just going to plug in 9 down here for x. So we get 2. Okay. All right. Let's see. One more. I'll just leave this on the screen for a second and see if you can do this. And then I'll just step through it without me talking to show you the solution. All right, so hopefully you're comfortable with a little different type of problem here. All right, let's do one more here, okay? Notice this time I'm telling you that it varies directly. Oops, hang on, let's go back. Okay, here we go. Varies directly with x and inversely with z, okay? So we've got 3 variables here, y, x, and z. So what would the function look like, right? So first we have to write it. Here's what it would look like. Since it varies directly with x, that's going to be k times x. Since it varies inversely with z, the z will go in the denominator. So notice we also have to have values for all 3, right? That's what we're given right here. So let's plug those in and then solve for k. Okay, so if we do that, first I solve for k here, just to rearrange it. Now I can plug in my numbers. So I'm going to put in 12 for y, 3 for z, and 9 for x. If If I do that, do the math, we get 4. Okay, so k is equal to 4. So here's our function, right, with our k value. And then the second part, it says find y when x is equal to 6 and z is equal to 2. So we're going to plug in here for x and z. So here's 6 for x, 2 for z. So 24 divided by 2 gives us 12. Okay, so a little more complex there in that we have 3 variables. One of them varies directly and the other varies inversely. All right, so that wraps up our lesson here. So we know how to identify direct and inverse variation, kind of how we defined each of those. We can write functions to model inverse and direct variations. So that includes first, which type of variation do I think I have, and then confirming that you have a consistent k value. And then the last part is, how can we describe combined variations, right? Where we have multiple variables, some could be direct and some could be inverse. Okay, so that wraps up the lesson for today. If you look in Google Classroom, you'll find a worksheet that goes with this. Go ahead and work on that, get that turned in, and we'll go over this next week online. All right, take care.